Still people are joining. So let's wait for 1 or 2 minutes. So I think you people have already done the algorithm course, data structure algorithm, CS204 or CS512. So have you heard of one term, network embedding or graph embedding? Hello.
Not heard, sir.
So network embedding. So not heard. So this is actually means a standard means the graph algorithm problem. So today we'll discuss the network embedding or graph embedding in terms of example point of view, not the group point of view, or what is the problem we'll discuss. Okay, so what is network embedding problem and how it can take benefit of that. So okay, now it's time. So I'll show you one photo maybe. Not the YouTube, so I don't require YouTube. So I want one photo only. So in the right corner, so save ours. So are you able to see my screen?
Yes, sir.
So what I am showing? So I am trying to show. So a train is carrying a lot of trucks. Okay, so what graph embedding also it's look at similar kind of thing. So just like tunneling. So you have some ways, and you means you want to take something else on that way. So it's kind of this is a train line, and we have put the truck on top of this train, and train is going. Ultimately, truck is also going. So in tunneling, it is a standard picture, but virtualizations also standard pictures. Okay, and what here also what similar kind of things, maybe graph embeddings. So we can refer similar kind of things. So something is given, and we want to run something else on top of that. Okay, so let's look at the examples on this thing. So network embedding. Let's see. So today's class, what we'll discuss: network embedding, Amdahl's law, and GPU. So these three things. What is network embedding? So and what is their usefulness? First thing is embedding allows us to use algorithm or program developed for an existing architecture. Architecture means network architectures. What I am saying means or topology, network topology on a new one. So suppose you have developed a algorithm for tree. Okay, tree kind of interconnections topology. Okay, so computer are connected using a tree tree patterns. We have developed the program to work efficiently in tree format, and then we want to run the program on the mesh architecture or some other architectures, and how to do. So use an algorithm or program developed for an existing architecture for a new one by simply letting the new one follow the same stage as older one. Okay, so this is a network. Embedding allows this thing. So in terms of, suppose you have written a MPA program, so which will work for, suppose, mesh. Okay, mesh network. Mesh network means the HPC system connected using a mesh topology. And if we want to execute the same program on another HPC where the network topology of that HPC is not mesh network, so it is something else, then how to do? So that is, the technique is called embedding. So by simply letting the new one follow the same step as older one. So how to do that thing? So let's discuss. And also embedding helps in application mapping to architectures. Embedding tree to mesh, running merge sort on a mesh. So if you look at merge sort by default, if you do a parallel program for merge sort, then it will be default kind of tree kind of structure. Okay, and if you want to run a mesh, how to do mesh? So embedding tree into hypercube. Embedding mesh into tree. Suppose you want to do a matrix multiplications. Matrix multiplications by default it uses actually two-dimensional structure. Okay, naturally matrix multiplication will be two-dimensional structure. Suppose you want to run the matrix multiplication applications, which is written for mesh kind of topology, HPC system mesh kind of topology, and we want to run the same program on a tree kind of structure. How to do? So this kind of methodology, how we can achieve or do these things on a different architecture, that process is called embedding. Okay, so example, let's say very simplistic example. So let me connect this. So are you able to see the screen? Na? So here, this is a tree with 7 nodes. Okay, so 0, 1, 2, 3, 4, 5, 6, and 3, 4, 5, 6 are leaf node, and 0 is the root node. Okay, and this is a simple tree, and we want to embed this into a mesh. Embed into a mesh. This is a how many node? These have 7 node, and these have how many node? This is 9 node. Okay, so 9 node and number of links also, you can see more number of links are there. So clearly we can embed this tree onto this mesh very nicely. Okay, so we can use this 0 can be mapped to this place, 0 is mapping to this place, then age 1 is mapping to this place, then 2 is mapping to this place. This is a same tree. We can replicate this thing because we have this 7 node tree, and this is a 9 node mesh, and it is very nicely we are able to map to this mesh 2 tree. Okay, so just simply means assume, so this 0th node is mapped to central locations, then 1 is left one, then 2 is right one, then 5 is, this is left, and 5 and 6 is again from 2, 5 and 6 is mapped like this. So we can run simply means assume, suppose this is a node serially, suppose node is let me do a different kind of node representations, A, B, C, then D, E, F, then G, H, I. So suppose there are this 9 node named A, B, C, D, E, F, G, H, I, or directly then 0 is mapped to E. Then similarly, just say we want a mapping, high level mapping, and whenever you're running a tree algorithm on mesh, so instead of using this mapping, so it will use the virtual mappings. Okay, so whenever it 0 is corresponding, it will map to E. Okay, so it will corresponding to E. So in that way, you can run tree algorithm on mesh very nicely. And what is a good embedding? So there must be some way. Okay, some way. What is a good mapping or embedding techniques? So this embedding, what is embedding? It is clear. Hello.
Yes, sir.
We're trying to run means tree application on mesh, or one application written in for some topology, you want to run in another topology. So you want to run it, suppose you have written a program for our HPC, suppose permission HPC, and it is one kind of network, and we want to run the same program to another HPC in suppose in ISC Bangalore. So there is another HPC, but that may not be the same network. Topology may not be the same one. Okay. So what are the means embedding? So means what are the what I can say parameter defines the good embedding process. Okay. So embedding at the richness, there is a concept called dilations. So whenever you're mapping, so one network to another network. So this is one topology to another topology. So dilations, longest path onto which an edge is mapped. Okay, longest path onto which an edge is mapped. Okay, this is dilations. Second one is congestions. Maximum number of edge mapped to one edge. That is congestion slowdown or contention slowdown. What do you say? Contention slowdown. So whenever you are mapping, so in this case, so one node is mapped to one node of source is mapped to one node of target node. One edge of source is mapped to one edge of target. Okay, and one node, one edge, and every edge of this also, every edge of source is mapped to one edge of the destination. So in that case, all this parameter is one. So that means it is a very good embedding. So there is no slowdown. So dilation is longest path onto which an edge is mapped. Congestions, maximum number of edge mapped to one edge, and load factor is maximum number of node mapped to one node. That is a load factor. That is processing slowdown. So what trying to define three parameters: routing slowdown, congestion slowdown, contention slowdown, and third one is processing slowdown. Finally, three term dilations, congestion, and load factors. And in these previous examples, all the three parameters are 1, 1, 1. So in this case, so all the parameters dilation is equal to 1, congestion is equal to 1, and load factor is equal to 1. That means routing slowdown is also 1, contention is also 1, and processing slowdown also 1. That means there is no issue. Okay. But whenever, suppose you want to, this is a 3x3 mesh. Suppose you want to do a means 4x2 mesh. Suppose you want to do the 4x2 mesh. So in this case, what happening? So suppose you try to map, but in this case, one example of mapping. So in this case, 0 is mapped to this place. So this 0 is mapped to this place. Okay. A is mapped to this side. B is mapped to this. That means this is 1, 2. This is fine. But in this case, suppose 3 is mapped to this place. 3 is mapped to this place. So 1 and 3 is fine. But for 4, so here 4 is connected to 1. 4 is connected to 1, but there is no scope where 4 can be connected here directly. That means 4 need to means a connection from 1 to 4. Connection from 1 to 4, this D need to go through one more, what I can say, node. That means here one edges is mapped to two edges here. Okay, here one edge is mapped to two edges, and another thing is this edge. Here 1 to 3 edges. These edges, it required to transfer data for 1 to 3, also 1 to 4. That means, so load factor is definitely 1 because we have enough number of nodes, so there is no issue. But one thing is longest path to which one edge is mapped. So here, this D, edge D is actually mapped to two edges of the target one. So that means routing slowdown. So this is 2. Okay, and then maximum number of edges mapped to one edge. So in this case, these edges. Are you able to see this thing? So these edges, we are mapping C, also we are mapping D. So in target architecture for this edge, we are trying to map this and this to one edges. Both this and C and D mapping to these edges. That means here contention also there. So for this edge, there is a contention, and for this edge, it is one edge of source is getting two edges of destinations. That means it is getting elongated. So it is one is dilation is 2, congestion is also 2. Okay. So in this case, dilation is 2 and congestion is 2, and load factor means every node is mapped to individual nodes. So there is no processing slowdown. But routing slowdown is there, congestion slowdown is there. Is this clear?
Can you explain dilation again?
Yeah. Dilation means longest path to which an edge is mapped. So in this case, in this example, so this edge, so particularly edge DH, this DH is here we cannot, because we have already mapped 1 to here and only 1 edges can be mapped, 3 can be made, but for 4 we don't have direct neighbor, free neighbor, because already we have mapped 0 and 3. Okay, we don't have direct neighbor from 1, so we need to map to little bit distance one. So that's why this 4 is mapped here, and for HD of the source is getting to 2 edges of destinations, then 2 edges of the target network. So that means this DH here it is 1, but whenever you are doing the embedding, this DH is transformed to actually 2 edges. That means there will be a routing slowdown because this D path single hop, now it is getting converted into 2 hop. It is clear?
Yes, sir. So the edge between 1 and 3 node is being used for 2 edges in the tree, right?
2 edges. That is called congestion.
So data is being sent parallelly, right?
Yeah, that is congestion. So this target C edges is used by this C edges, also D edges of the source. That means this connection, this link is shared by 2 source link. That means congestion also 2. Is this clear?
Yes, sir. Thank you.
Yeah. So let's look at another embedding, same example. Okay. So now we have reduced to 2 cross 2 mesh. So now it is a number of nodes is also less. So in this case, here 7 nodes, and here total number of nodes is 4. Definitely in target architecture we have only 4 nodes. Definitely there will be processing slowdown. Okay, so what we are doing here, 2 source node are mapped to 1 node of target. So 01 is mapped here, then 25 is mapped here, then 34 is mapped here, and then 6 is mapped here. Okay, so which edges is mapped however? You will look at 01. 01, anyhow this edge is getting removed. 01 is mapped to same guys, so we don't require. But 02, so 02 this one, this is mapped to this guy, because 0 is mapped to another node and 2 is mapped to different node. So this is edge B. Here CD, so 01. So this is C and D. This 3 4 from 1 it is 3 4 it is mapped. Okay, and from 2 okay, so we have 5 and 6. For 5 anyhow it is mapped to the same places, each getting 0, so we don't require anything, but for 6 we require F. So in this case, in general, means whenever 2 edges map to a same guys, so suppose this in this case 01 and 1 map to 1 node, that means these communications can be done very efficiently, but thing is that there may be processing delay. So whenever we are getting benefit, we don't what I can say, but whenever we are getting loss, then only we see. Okay, mostly what is the loss? And so we are trying to define in terms of loss. So in this case, what is the dilations? Longest path to which edge dilation will be
1.
And what is the means the congestion?
2.
C and D are mapped to same line.
So C and D, and load factor also it will be 2. Load factor means how many nodes, source node is getting mapped to target node, the maximum number we want. So in this case, 2 node mapped, 2 node mapped, 2 node mapped. So here load factor is also 2. So dilation is 1, congestion is 2, and load factor is 2. So how good the quality of embedding? So this defines. Okay. So this is a very simplistic examples, and this network embedding is actually a very good theoretical topic. And given a source topology, if you want to map to any target topology, what will be the embedding and what is the best way to do embedding? So there is a, whatever you have done is with example based. How to come up with this embedding? So this is first thing. And second thing is how to come up with good embedding and what will be the algorithm. So we are not discussing algorithm, best embedding algorithm here and proving of algorithm. So there is a separate research area for network embedding or topology embedding. Okay, so I am giving the pointer. If you want to read more, then just go and read that. Okay, so just Google search topology embedding, you will get a lot of actually theoretical papers, theoretical research. So in this course, only it is limited to only some examples and how embedding will help us in running one applications written for one topology will be easily you can put into another topology. Okay, so we have written a HPC applications for one supercomputer can be easily run or nicely run on another supercomputer. Got my point? So this finishes here once our network embedding, very simplistic with examples. Okay, so next we'll move towards performance of parallel program. So this is Amdahl's law. The very first class people describe the Amdahl's law, but we are describing this Amdahl's much later. Okay, but still we need to describe the Amdahl's law. Okay, so what is Amdahl's law? So we have given this example. So this example, OpenMP examples. So OpenMP example have many serial sections and parallel sections. Are you able to see this thing? So this is a serial one. Then this is a parallel for loop. Then another, this one is M is equal to 500 serial one. Then again another OMP parallel for loop. Then this is done. So if you look at in this case, there are 2 parallel sections and 3 serial sections. This is clear? So in this,
yes, sir.
Yeah. So 3 serial section and 1 parallel sections. So let's take some standard how given a program how we can achieve the efficiency, how we can calculate the speed up and efficiency given the serial fraction and parallel fractions. Okay. So speed up and efficiency. So notion. Let's look at some notion. Suppose T1 is the time. Suppose you execute the program on actually uniprocessor, and TP is the time on P processor. Suppose execution time on P processor. Then what will be the speed up? Definitely speed up will be T1 by TP. So suppose on one processor it is taking 1 hour. Okay, and on 10 processor, suppose it is taking 5 minutes. Then what will be speed up? So 60 by 5, 12. Okay, so speed up means time on uniprocessor divided by time on P processor. Okay, parallel processor. So speed up is T1 by TP, and which is usually less than number of processor. So usually, what I'm saying usually. Okay, so and what will be efficiency? Efficiency is EP is equal to T1 by PTP. Suppose you are using 5 processor. So what I'm giving examples. Suppose T1 is equal to suppose 100, and P is equal to suppose number of processor you are using 10. So T1 is equal to 100 and P1 is equal to P is equal to 10 and running on 10 processor. Okay, TP. Suppose you are getting 20. So what is speed up? Speed up is equal to 100 by 20. Speed up we are getting 5. What speed up we are getting? 5. You are using 10 processor, getting speed up 5. You are using 10 processor, getting speed of suppose 5. Okay, then what will be the efficiency? Efficiency is
0.5.
efficiency is 0.5. So 10 processor are getting speed of 5. So in that way. So if we calculate using the formula, so 100 by 10 into 20. So this 10 into 20, this one is same thing. So this will give you same 5 by 10. So how much speed up we are getting? That means it is speed up by P, SP by P. Okay, so ultimately efficiency is SP by P. So SP by P. So if you are getting a 10 speed up on 10 machines, then it is efficiency is 1. But in general, usually speed up is less than P, and we can say efficiency will be less than 1. Okay, and in general, what happens? Speed up is less than P and efficiency is less than 1 due to overhead. So because parallel and running parallel, there's some overhead, we will not get speed up greater than equal to P. But sometime we may get superlinear speed up. Okay, SP may be greater than P or EP greater than 1 because we may suppose you are for parallel algorithm. So suppose you are solving some problem. Okay, and for parallel algorithm, parallel architecture, you are using a different algorithm, and for solving sequential one, you are using different algorithm. Okay, so failure to use the best sequential algorithm, then definitely your parallel case will get better speed up, but means less execution time. And another thing is sometimes advantage due to larger memory. Yeah. Any questions? Sometimes advantage due to larger memory. So I'll give you the what is the advantage due to larger memory. So suppose you are running a applications on your dual core. Suppose you have a machine. Nowadays all i5 machines are actually 6 core. Okay, and suppose two machines. Suppose i3 machines you take. Let me put. Suppose you take i3 machines. Okay, so i3 machines in general we have actually 2 core 4 threads. So ultimately 4 core machines, and i7 machines are actually 8 core 16 threads. Okay, so this is the standard. So ultimately 16 core machines. Suppose or if you run a program on i3, okay, and i7. So in general, whenever this i3 they develop, i3 have actually smaller cache. So memory will be in this case 1 MB cache i3, and in this case it may happen that it may have 4 MB cache. i7 have 4 MB cache because they are putting 8 cores, so or 16 ultimate core. So they put larger memories. So some applications may have, if you are running with 1 MB cache, it may perform very, very badly. But if you are running with actually 4 MB cache, it may perform very nicely. Okay, so the speed up we are not getting from the actual processing side, maybe if you are getting from the memory sides. Then you may get a superlinear speed up. Suppose running on 4 core, you are getting suppose at 10 seconds, and running on actually 16 core, supposed to be divided by 4, but you will get in, maybe you can finish in 1 second. Because it may fit into the 4 MB cache. Okay. Advantage to larger memory may give you superlinear speedups. Whenever I say linear means it is 1. Okay, speedup is 1, and superlinear means it is more than 1. And what is Amdahl's law? Suppose given a program, so we have many serial sections and parallel sections. So suppose this same examples. How many serial sections? How many parallel sections in this case?
3 serial section, 2 parallel section.
Parallel. Similar example I am giving. So in this case, let's take. So this is a one applications. So this is a one applications. So here we have 3 serial sections and 2 parallel sections. Serial sections are red color and parallel sections are green color. Okay. So total work is 500, time is suppose 500, and suppose you are running on one processor, so you'll get speed up 1x. Suppose same work, same applications, we run on two processor. Suppose try to run on two processor, then this parallel part, this green part can be divided into two chunks. Suppose this green part is divisible load. What I am saying divisible load means it can be divisible to any processor if available. Okay, the divisible load. Suppose this green part is purely divisible load. Okay, parallelly means divisible load. Then you divide the tasks into two parts, 50-50. Then again merge. Again you do serially. Then again divide the parallel part into two parts. So what will be the execution time? So total work is 500. Execution time will be 400. And what will be the speed up? Speed up is work is 500 by 400. So 500 by 400, what you are getting speed up? 1.25. Suppose you make it 4. So this anyhow serial sections, anyhow this time will add up. So in this case, 100, 100, 100, 300 plus 100. So total 400. In this case, 100, 100, 100, 300 plus this 50. So this is 25, 25. So totally 350. So what speed up we are getting? 1.4x. We are using 4 processor, but we are getting 1.4x. Suppose these things continue. You try to increase into infinite number of processor. So infinite number, if it is fully divisible load. What I am assuming is fully divisible load. So this parallel section is fully divisible. Any number of processor, you can divide the work, suppose. Theoretically. But it may not be possible, but theoretically I am saying. So if you have infinite number of processor, then what will be the time? So approximately 0. So this for this parallel sections for infinite processor, it will be approximately 0. For this parallel sections, it will be approximately 0. And what will speed up you are getting? So what will be the total time? Can you go less than 300? Absolutely no. What will be the time taken? It will be 300. And what speed up will get? 1.7x. Even if you are using 10,000 or 1 million processor, you may not get more than 1.7 speed up. So who is limiting?
Serial section of the code is limiting.
So because of the serial part, so out of this 500 work, 300 need to be done serially. Out of this 500 work, 300 work need to be done serially. And that is the bottleneck. And you cannot get speed up more than 1.7 because of that reason. So let's formalize the serial fractions. So let's serial fractions S. Okay, S is equal to TS by T1. So serial fraction of the work. So in this case, what will be the example? In this example, what will be serial fractions? So T1 is equal to 500 and serial fraction is 300. Okay, so 300 by 500. So what in this case, previous example, serial part is 300 and T1 is 500. In this previous example, this is serial fractions. And TP is equal to total execution time in parallel processor. So it will be anyhow this serial part, this 300 plus T1 minus TS, that is 500 minus 300 by P. So only this 200, this 200 we are dividing into processor, but this 300 is still for every processor. So whatever is the number of processor, this things is not reducing. Only this part is reducing. 200 by 3, 200 by 4, 200 by 5, 200 by 100, 200 by means million. So what are the P is equal to suppose infinite also. But still this 300 will continue. So ultimately, what is the speed up? Speed up SP is equal to T1 by TP. And if you divide, this is the T1 same thing. And what is the TP? So parallel time on P processor. Time on P processor is same thing. So T1 by TS plus T1 minus TS by P. And what you are trying to say, it is rearranging the things, nothing else. So TS by 1 minus P, 1 minus 1 by P plus T1 by P. Okay, so this is the speed up. And if you do a little bit more, then what you are getting? So this thing. Okay, so this same thing we are carry forward here. And if you look at T1 by TS, what is T1 by TS? So in this case, what we are trying to do? So T1 by TS plus 1 by P plus T1 by P. So if you just S, what is S? S is equal to TS by T1. Okay, S is equal to T1 by TS by T1. So these things, these terms, so this term we are simply writing. Okay, so what we are trying to do in this case also, we are dividing by T1. This also divided by T1, and this also we are dividing by T1. So this by T1. So everywhere we are dividing by T1. So then what will we get? So this place TS by T1 will be S, and this will be things. So SP is equal to speed up is equal to 1 by S, 1 minus 1 by P plus 1 by P. Okay, and if you rearrange, you will get this thing. But from this sides, from this part, suppose P is infinity. So suppose you make P is equal to infinite, then what will you get? Suppose in this case P is equal to infinite. If you make P is equal to infinite, what will you get? So ultimately this part will be 0, this part will be 0. Then speed up is limited by 1 by S. So in our earlier example, what is S? S is 300 by 500. So speed up will be limited by 500 by 300. This is S. So ultimately, so whatever the number of processor you take, speed up will be limited by 1 by S. So in this case, this will be 1.7. What are the examples? 1.7. So it will be limited by 1.7. You cannot go beyond that because speed up is limited by the serial fractions. So if your program have more amount of serial fractions, then you cannot parallelize and you cannot get better speed up. If a program or if applications have serial fraction is very less, okay, suppose 2% or 1%, then you can get a very good speed up. Okay. So this graph shows speed up, and this is serial fractions. If serial fractions increase, then speed up will not get. Okay. So this is as P is equal to, suppose S is equal to 1, then you will not get at all speed up. Okay. S is equal to 0. Suppose serial fraction is absolutely 0, then you may get linear speed up theoretically. If S is equal to 0, suppose S is equal to 0, then speed up we can may get linear speed up. Okay, but if S is equal to 1, so there is no scope to do parallelisms, then we will not get the speed. It is clear? Hello?
Yes, sir.
Yes, sir.
So this is the standard in doing parallelisms. So we should look at the what is the serial fractions and what is the parallel. Okay, and another assumption, whenever you are designing the Amdahl's law, suppose even if your parallel sections, suppose your parallel section is 80%, So suppose S is equal to only 0.1 and parallel section is 90%. Okay, S is equal to 0.1 and parallel section is 90%. Still, this Amdahl service still is very, what you can say, with many assumptions we have defined the Amdahl. So what are the assumptions we took? So let's look. So assumptions behind Amdahl's laws are all processors are homogeneous processor. So this is first thing. So in this earlier formula, so all processor will take homogeneous processor. All the communication costs are 0. So whenever they try to divide the work, so it is all divisible work and communication cost is 0. But in actual, it don't happen. And all the memory access time take unit amount of time. So parallel random access machines. So these assumptions and all the parallel sections are purely parallel and divisible load. So with these 4 assumptions, we came up with this formula. Okay, but whenever you relax one after another, then what will happen? So our this assumptions, if assumptions are true, then only this Amdahl's law can apply. So if you relax the assumptions, suppose all the memory access don't take unit time, then what will happen? So memory hierarchy, suppose cache memory, and suppose applications A run on 2 GHz Pentium 4 uniprocessor takes 10 minutes, and same applications run at 2 GHz i5 processor, suppose quad core, may run faster than 4x. Suppose this is uniprocessor, this P4 is whatever saying uniprocessor, and this is Intel i5, whatever saying is quad core. So this is 1 core and this is 4 core, and this application may run faster than 4x. Faster than 4x means we are using 4 processor, earlier it is 1 processor, now it is 4 processor. We may get super linear speed up. Earlier case was 1 MB maybe, but now in i5 we may get 4 MB and whole applications may fit into cache. And there is no capacity miss and other things. Because of that, we may get what I can say super linear speed up faster than 4x. So that means if all memory access takes unit execution time, then only it's valid. Architecture should be exactly same, then only it will be valid. And whenever you are increasing number of processor, then it will increase the cache or memory, and it will create the what I can say that assumptions it breaks. Okay, so if you assume all the memory access take unit time, then only it is valid. Otherwise, you may get super linear speed up or maybe different result. And another assumptions what we made, all communication costs are 0. So whenever you look at OpenMP or pthread creations, fork and join takes significant amount of times. So what is the ideal scenario? So in deriving the Amdahl's law, we assume like this. For parallel sections, so we divide the work into 4 parts. Okay. But actually, so this suppose 4 processors are divided into 4 parts. But whenever actually run an OpenMP code or pthread code, it's required to do thread fork, assign the work and wait for the synchronizations. This is forking and this is barrier synchronizations. In actual scenario, it's not the what I can say actually divisible parallel load. There is some kind of fork engine and some overhead there. So this is ideal scenario. This is serial part 1, serial part 2, and this is parallel part 1. So for this kind of applications, this is ideal scenario. But in actual scenario, this happens like this: TS1, TS2 plus TP. This is parallel sections, and there is 4 GAN for join. So in this case, example, in this case, we are taking 4 processors. That's why we are writing 4. Okay, so this is barrier synchronization and forking also takes time. So in this case, maybe ideal will be 3 maybe, because we are doing for 3 and for own cases we are doing 1. But still the assumption is very ideal assumption we cannot take. In actual case it is different. Is this clear? Hello?
Yes, sir.
And another thing, so parallel thread accessing to the shared resources. All the parallel sections are purely parallel, divisible load. And we have just some days back we discussed. So whenever you do work parallelly or collaboratively, and whenever there is a shared resources, many things getting it, many threads access to a shared resources need to be serialized. That means parallel thread accessing to the shared resources make it serial, and using higher number of processor may need to collaborate and have more communications. And application parallel sections may not be scaled with processor. So always we may not get the divisible load. So suppose in earlier case, what we say is simply infinite number of processor we put. Because in parallel sections, they try to collaborate and make access to the shared resources. That means critical section problem arise only in the parallel part, not in the serial part. Critical section problem arise only in the parallel part. And whenever you increase the number of processor, so per processor work may be very, very small and it may create more over it. Okay, so this is parallel thread accessing the share resource. Suppose you are accessing a share resource. Suppose in these parallel sections, one particular variables or one file is, suppose file A is shared. Suppose file A is shared, and every threads want to write to that file. Then for that shared variables app, so it is supposed to be done in parallel, but everyone will execute serially. That means this is blue colored one is actually waiting for their turn and executing. Supposed to do in only blue part, only small part, but they are taking more amount of time. In actual scenario, with share resources, it actually increase the things. So 4 times the critical sections. Okay, so ideal scenario we use like this in Amdahl's law, but actually it happens like this. So Amdahl's law is very ideal things. Theoretically, it is very good model, but with in real life cases, it may not apply, but still it is a very good rough estimate. Okay. And another thing is all processors are homogeneous. So asymmetric processing environment, suppose one big core and many small, tiny or small cores. Suppose Intel Xeon a big cores and GPU have four. Suppose you have in a machine, suppose in your PC, suppose you have a means i5 processor and we have another graphics card, and we want to run the applications using this i5 processor and GPU card. So GPU card have actually 2000 or 5000, or nowadays this GPU have a 10,000 core also, tiny cores. Then because of this, this is not homogeneous. This P we cannot say it is for all processor it is same. Then this model will not work. For homogeneous environment it's fine. For heterogeneous environment it may not work. And whatever say we say grain size or processor size. So Intel CPU, okay, Intel core are bigger core, but number of cores in GPUs or graphics card are much higher number, but they are very, very small cores. So what you can say, 10,000 ants versus one big ox or elephant. Okay, suppose one elephant and 10,000 ant kind of thing. So for this kind of environment, it is not also theoretically you cannot use this formula. Okay, so these 4 cases we cannot use these cases, and this I'm just to assume these things. All are homogeneous core, all memory accessor, unit time, and whatever the parallel sections is purely divisible load parallel sections. Okay, and there is no communication time between them. So these are the 4 assumptions it make, and based on that 4 assumptions, they derive the formula. Amdahl's derive the formula, and it is a means not a bad formula, it is a very good formula. So for high level, it is clear.
Yes, sir.
Okay. So I am listening only yes sir from only one person. Tanvis. Other people they are not saying yes or no. It's better to listen from many people.
Yes, sir.
Okay. So what I am saying, grain size means whenever you increase the number of processor, then what happens? So suppose you have a means work is 500 unit, and if you are employing 4 processor, then per person's how much? 125 work per person. But if you are employing more number of person, then per person work will be limited. So in that case, you may get more unnecessary communications. If you have more fine grain one, so if you have more fine grain one, so then so if you divide the work into fine grain, then there will be more overhead. Okay, more overhead. And if you are dividing coarse grain, then you have limited parallelism and load imbalance will be there. Load imbalance will be there. So suppose you cannot divide into very smaller. Suppose you have 100 work. Okay, so 100 work, and you divide into chunk of 20. So 20 work can be given to one person. Suppose you can give to how many people? Only 5 people. Suppose you have suppose you have what I'm saying is 100 work, and you divided the grain size or chunk of work is 20, and suppose you have 5 people, then these 5 people can get one chunk, and everyone will finish because everyone get 20 work, everyone will get 20 work, and it will finish in 20 means whatever the take time, equal amount of time they can finish. Suppose you have 4 persons, then what will happen? So 4 person will get one work, one chunk of work, okay, one group, and one person will get 2 chunk of work. So he need to do, one person need to do 40 work, and other person need to do 20. So this will create load imbalance. This will create load imbalance. If the grain size is bigger, then it will create load imbalance. If grain size is smaller, then every time you need to redistribute the thing. Okay, so in that case, communications will be more. Fine grain communication will be more. Coarse grain means if you increase the grain size or chunk size, then means your load imbalance may occur. So there is a optimal grain size for every applications for parallel. If this slide is clear, suppose a work is there and we want to divide the work into multiple peoples, multiple worker. So how to divide? So very small work and lot of overhead in managing. Okay, so bigger chunk size, bigger group if you make, then there may be a load imbalance. It's common thing. Okay, so whenever you write parallel program work divisions, this applies. Okay, so now what is the time? So 3:53. So let's move to our new topic still. Maybe there is another topic called GPU. So have you heard about the term graphics card?
Yes, sir.
Yes, sir. Excuse me.
Yeah.
Excuse me, sir. Sir, before moving on, in the last slide, here like when I increase the grain size, no, when I decrease the grain size, what exactly is the problem?
So whenever you decrease the grain size, that every time you need to give the work to people. So
basically, my communication cost is very high. Right?
Your management will be more.
Sorry?
Management, you need to management will be more. Every time one processor, you can give actually very small amount of work, suppose.
Okay, yeah. And
Many
that is
times
what I want.
the processor, and many times you need to get the communication. Whether they have done the work or not. After they finish the work, they need to supply the work. If you are giving very small work, then it takes actually more time.
Okay. Thank you.
Unnecessary overhead.
Sorry, sir, it's like dynamic scheduling, but with a very small size.
Small size, then it will be actually create more overhead.
Yes.
Okay. So सपोज आप बफेट डिनर पे जाते हैं और आपके वो चम्मच पे जाता है, जो खाना जाता है दाल देना, वो छोटे चम्मच यूज करता है, तो आपको बार बार जाना पड़ेगा ना. So that's actually create unnecessary overhead.
Yes,
So you need to use optimal chambers size. You got my point? You need to use optimal chambers size of grain size.
yes, sir.
So if you use a very big chamber, then what will happen? So many people take and they will waste their food. So low imbalance will occur. So this is very simple logic. Okay, so we'll move towards GPU. So let's see time. 5 minutes we have. So 5 minutes we can do a lot of things in 5 minutes. So GPU, have you heard about this graphics card? So in general, graphics card, we put graphics card on our PC. Nowadays in laptop also have graphics card, and also mobile also have some graphics processing unit. Okay, so everywhere graphics card is, we cannot get rid of the graphics card. Okay, so wherever you go, you will find the graphics card. Okay, so wherever means any high-end processing nowadays, graphics card is must, whether it is external or detachable or inbuilt or inside the chip. Anyhow, we cannot get rid of this. Anyhow, they'll be there. So graphics card in motherboard. Now the most important thing is let's consider the graphics card. Suppose you have a PC and you have installed a graphics card on top of that on your motherboard. Okay, so in PCI slot. So to isolate graphics computations. Earlier days it was fixed purpose. So only for graphics purpose it was supposed to do only graphics. Okay, and at that time we call that as accelerator, application specific accelerator for graphics applications. But nowadays there's graphics processing engine or GPU are programmable and configurable. So whenever it is programmable and configurable, that means we can use that GPU for not only the graphics purpose, but for the general purpose also we can use. Why not to use the same for general purpose? Because graphics computations have some kind of computations where very small repeated functions get called. Just like ray tracing applications or rendering applications, we need to call the very small functions repeatedly. And many general applications we have also similar kind of characteristics. If that kind happens, then why not to use GPU for the general purpose for that kind of applications? So that's why nowadays GPU are getting used for general purpose also. So have you heard about the CNN, DNN, neural network computations? Nowadays all neural network computations, tensor computations, matrix computations getting speed up by GPU. Even Python code. Okay, so Python library also they are trying to use GPU. Okay, so why not to study a little bit of GPU in high performance computing course? And it will be only for one class. Okay, not more than that. One class it will be sufficient. And suppose in general in GPU what happens? You install a GPU on your card. Okay, on your PCI slot of your motherboard. Then in general OS see different address space. Whatever OS use address space, your program use address space, and what are the graphics card address space, graphics computations address space will be different. So they use distributed memory programming, not the shared memory. So suppose you want to do some computation on graphics card, then you send the data, do the computations, get back the result. Okay, this is distributed memory computations. Both address space are different. Okay, so host address space, host have 16 GB of RAM. Here address space will be different. Card have 16 GB, another 16 GB. Their address space will be different. This address space are not shared in general, but nowadays people are trying to share the thing also. Okay, and this is last slides. What is CPU and what is GPU? So have you heard about GTX 3090? Any graphics card have you heard about? This is
Yes,
one of the
Yes, sir.
so RTX 3090. So this is around 1.3 lakhs. If you go and search in Amazon, you will see. And these are actually around 10,000 core. Whenever you say 10,000 core in a small graphics card, how much big core will be? Just like Kide just like ants. So it will be very, very small cores. But for some applications, this will give huge performance. Okay, so GPU versus CPUs, and GPU have actually big 4 cores, and CPU right side, it have huge number of very, very small core. So same area, but we are able to see huge number of cores. So GTX 3090, NVIDIA, this is NVIDIA one. I'm not advertising NVIDIA, but taking some examples. So these have actually 10,000 cores, 24 GB of DDR6, And for some applications, graphics applications or matrix multiplications or tensor core kind of or CNN, DNN, you can speed up around 100 times or 200 times in GPU. So why not to use? Okay. So how GPU works? What is the philosophy behind the GPU? And how we can do on the top. So that we'll discuss in the next class. So tomorrow we'll not have any class. This is announcement. So tomorrow, this class, tomorrow class will be postponed, and we'll take the makeup class later. So it will be announced. Is this clear?
Yes, sir.
Yes, sir.
So
Yes, sir.
I will come in the MS team
Yes, sir.
group link also. So tomorrow we'll not have any class. So Thursday I'm going out of town.
Okay.
Any questions?
So, sir, now programmable. So now we cannot say them hardware accelerator.
No, we can call it hardware accelerator. Only thing is these are not ASIC. These are not fixed one. So earlier days it was fixed purpose, but nowadays it is programmable. Still it is accelerator.
Okay.
Accelerator can be fixed purpose or accelerator can be programmable. Whenever you say accelerator, there is a separate guide or separate what I can say unit which can do faster way. That is called accelerator. Okay. So whether it is programmable or fixed. So in the mobile SoC,
So
many
what
things
is
are
this PCI slot?
programmable and many things are fixed. Yeah. Hello.
So what is this PCI slot? I've seen this written at like many places now. Many sites, references, motherboard, PCI slot. So what is this PCI slot?
So PCI slot means this exact term. So it's communication interface, parallel communication interface. I think so. So I also need to go and check. So it is a PCI slot means in your PC motherboard. Okay. So there is an interface where you can put the graphics card. This are you able to see my screen? Let me put the pointer. So this thing actually PCI interface. So from external loop. So internal protocol may be different. Okay. There is a standard protocol PCI. Okay. PCI slots we get, and internally it works in a different protocol. Let's follow some specific protocol, PCI protocol.
Okay, so different these
Actually
components
communication
are connected to.
It is a communication interface, just like another clock. Okay, these have actually many lines or many connecting lines. So 16 connecting line or 64 connecting line. For different, it will be different.
Okay, sir.
So in every means laptop and PC, so they have PCI slots, and some PCI slot size will be smaller. In laptop, the size will be smaller, and PC size will be bigger. Some are 16x or 8x or 4x. This is depend on size. But it is communication interface, so you can put your external card on top of that. So nowadays all memories, SSD memories, they're coming with PCI slots. So have you heard about the SSD in your either a MacBook you take or modern laptop you take? So nowadays coming with SSD, and this SSD they are actually means interface is not the SATA the standard ATA whatever you say, but now they are doing with PCI. PCI have actually more number of lines, that means communicating lines. Worse. So 64 or 128 parallel line will be there, so that you can get the data transfer very, very quickly. Is clear?
Okay. Yes, sir. Thank you.
Okay, thank you.
Thank you, sir.